2nd, 9:44 p.m. Um, I hope you're doing good on this Tuesday night. And this video is going to be called Summer 7. Chapter 7 chapter 2 is one long chapter. So I figured I might as well get another part of it done tonight, and then I'll get the rest of it finished tomorrow. We left off talking about seafloor spreading and Harry Hess and Robert Dietz. We talked about the mid-ocean ridges that span the globe like stitches on a baseball. We talked about volcanism occurring in a rift. That's a huge valley actually at the center of this mountain range in these mid-ocean ridges. And as magma rises, you have underwater volcanism occurring here at the mid-ocean ridges. In other words, what's going on is you're making new sea floor. And the sea floor spreads apart like two conveyor belts, pushing continents away. So some continents end up becoming farther away than others and pushing other continents together. And this all happened back in 62 when this theory of seafloor spreading was introduced to the scientific community. And it was a validation of Wegener because they showed that continents could move. But after 1962, you still had people who wanted to believe in permanism, and more data was needed to test whether or not the continents really were moving and whether or not seafloor spreading was occurring. So JOIDS, I mentioned JOIDS earlier on, the Joint Oceanographic International Development Exploratory Society, of all the countries in the free world, United States, France, England, and our former enemies, Germany, Italy, and Japan, joined in, all the democracies in the world, to test this new theory of seafloor spreading. Now, think about it for a moment. There's a way. How would you test this new theory? If seafloor spreading was really occurring, then shouldn't we be able to tell by dating the rocks, finding out how old they are? If seafloor spreading is truly occurring, we should see that the youngest rocks on the seafloor are at the center of the mid-ocean ridge, and that older rocks are found farther away from the mid-ocean ridge. And when when the oceanic lithosphere gets even farther away, the rocks should be older, and these ages should be symmetrical on both sides, like stripes. Well, let's see if that happens. Here's the actual data that they came out with back in the 60s, and the orange rocks are the youngest, the yellow are the second youngest, the green are the third youngest, and the oldest ones are blue and purple. And the age distributions are symmetrical. That means the same on both sides. Exactly as predicted by by seafloor spreading, right? So even the most skeptical people had to admit that this data is exactly as predicted by the seafloor spreading theory. If permanism was true, you just see that you wouldn't see any geometric relationship between these mid-ocean ridges and the ages. And a lot of the people who collected the data believed in permanism, but they had to go with what the data actually showed. Another thing that came about from the permanism people was, well, you guys who claim that seafloor spreading is occurring have a problem. They would say. They said if the seafloor, if new seafloor is being formed at the mid-ocean ridges, and it's moving apart, shouldn't the Earth be expanding like a balloon filled with helium? Yeah, but the thing is, Harry Hess and Robert Dietz already had the answer to that. Notice what happens to the oceanic lithosphere when oceanic lithosphere hits the continents. Remember, we talked about the oceanic crust being denser, heavier, because it has more iron in it. Due to its heaviness, it would sink into the earth, into the mantle underneath the continents. This, ladies and gentlemen, is called subduction. So when oceanic lithosphere is pushed against continents, oceanic lithosphere subducts underneath the lighter weight continental rocks, the lighter density continental rocks. And there's always a deep ocean trench that marks the spot of the subduction. Let me show you what that is. Deep ocean trench. These are the deepest parts of the ocean. So when you have subduction occur, as you can see here, there's a deep ocean trench that marks the spot of the subduction. So Hess had the answer to his detractors even before they had brought it up. The reason why the Earth is not expanding is quite simple. He knew it was coming, and just like he had his answer ready. The new sea floor that's being formed at the mid-ocean ridges is being destroyed as it's subducted underneath the continents. That's why the Earth is not expanding. And so it was another nail in the coffin, so to speak, for the people who believed in the old idea of permanism. Here in the year 2020, there's not a single geologist that you will ever meet who believes in permanism because the data is just too overwhelming. In the 60s, the British decided to do their own studies to see if seafloor spreading was really occurring. And as you know, in our country, we have our great centers of learning: Harvard, Yale, Stanford, Caltech, MIT. Well, the British have theirs as well. They have Oxford and Cambridge. And in Cambridge University, there was a Professor Matthews and his graduate student who had the last name of Vine, Vine, and Matthews and Vine wanted to see whether or not seafloor spreading was occurring. And they decided to use paleomagnetism to determine whether or not seafloor spreading is occurring. Now, what is paleomagnetism? Well, first of all, we have a magnetic field around our planet. And you can clearly see it if you have a compass. The compass needle is going to point north, right? That's because of Earth's magnetic field. Where does Earth's magnetic field come from? It comes from the spinning of the liquid outer core. That produces an electrical field, which produces a magnetic field. Electricity produces magnetism. We've known that since the late 19th century with Faraday's experiments. So bottom line is we have a magnetic field and Earth's magnetic pole is pointing north. Right? Well, if you go back 1,600,000 years ago, Earth's magnetic field is pointing south. How do we know that? Because if you look at 1,600,000-year-old rocks that have magnetic minerals, they point south. 3 million years ago, Earth's magnetic field was pointing north. 4.5 million years ago, it was pointing south. 6.5 million years ago, it was pointing north. 7.2 million years ago, it was pointing south. What this clearly shows is Earth's magnetic field reverses itself. So sometimes the magnetic minerals are pointing north, and during those times, like at the present time, we call those times of normal polarity because it's normal to us to have a magnetic North Pole. However, when the Earth's magnetic field is pointing south, we call those times of reverse polarity. Someday, the Earth's magnetic field is going to reverse itself again, and then we'll have a magnetic south pole and reverse polarity. So Matthew and Vines had a hypothesis. They said if seafloor spreading is actually occurring, we should see stripes of positive polarity parallel to the mid-ocean ridges, followed by stripes of reverse polarity, positive, reverse, positive, reverse, positive. So you should see stripes of positive and negative polarity symmetrical on both sides of the mid-ocean ridges. What does symmetrical mean? Well, look at my face is symmetrical. If I put a line right here, one side of my face is almost a mirror image of the other side. So let's take a look here at the actual results. And see what they got. Okay, look at that. Man, it's exactly as predicted by seafloor spreading. Positive polarity, negative, and even the thickness of the stripes is the same on both sides. It's exactly as predicted by seafloor spreading. I challenge you to find any way to produce a pattern like this without seafloor spreading. So the paleomagnetism supported the new theory of seafloor spreading. The age data supported the theory of seafloor spreading. Um, People started to realize that it must occur. Seafloor spreading must occur. So the next thing that they wanted to figure out is subduction really occurring. Now imagine what happens when subduction occurs. Let's say we have oceanic lithosphere, which is denser, colliding with a continent. What happens? Well, the oceanic lithosphere sinks into the mantle and you form a trench, right? Imagine that. The oceanic plate is going to subduct underneath the continents. And as it sinks into the earth, it's going to put pressure on the surrounding rocks. We call that stress. Stress is equal to force divided by unit area. What is stress? Well, if I put enough pressure on this, enough stress on this, it's going to break, right? Rocks are the same. When you stress out rocks, they'll break. If you take a concrete bench and hit it with a sledgehammer, it's going to break, right? Force divided by unit area, stress. So if subduction truly occurs, we should see as the oceanic lithosphere subducts underneath the continents, it's going to stress out the surrounding rock. We should see that stress makes earthquakes. We should see earthquakes shallow, and then as the plate subducts, we should see deeper and deeper and deeper and deeper earthquakes. And a Russian scientist predicted that that's what we would see if subduction truly is occurring. Wow, look at that. See these X's? They represent earthquake epicenters. Earthquake epicenters begin shallow. That's where the earthquake begins at the trench, and then they're deeper and deeper and deeper following the subducting oceanic plate. Exactly as predicted by subduction. So the whole thing works. Everything was falling into place. It was becoming clear that seafloor spreading and subduction was occurring all around our planet. This was eye-opening, to say the least. So 1967, next, remember this man here, J. Tuzo Wilson. He's the one who came up with the theory of plate tectonics. He brought together seafloor spreading with Alfred Wegener's original idea of continental drift. And he published A map. And here's that map. And I showed it to you earlier with all of the plates. The entire planet is covered by plates. Where are we in the great state of Tennessee right now? We're right on the North American plate. Here's the South American plate, the African plate, the Arabian plate, the Indian plate, etc. These lines are places where the plates meet. For example, the African plate meets with the North American plate right here. And these are called plate boundaries. These, ladies and gentlemen, are real important to remember. Plate boundaries are the places where plates meet. The plates can push against each other. Sometimes subduction occurs, and you're going to get a trench. The plates can be pulled apart, like in mid-ocean ridges. They can move apart, or they can slide next to each other. There's only three ways that it works. A plate can push. I wish I had. Let me get some props here. Imagine that here's a plate, and here's another plate. I could push them together, and subduction can occur, and you get a deep ocean trench. Or I could pull them apart, like at the mid-ocean ridges, and then they move away from each other, or they could slide next to each other. Those are the three. Those are all plate boundaries. That's what these blue lines represent. Wherever the plates meet, you're going to get stress because if they pull apart or slide next to each other or push against each other, you're going to get stress, force divided by unit area. And therefore, you should get earthquakes, right? So if Tuzo Wilson's theory of plate tectonics was true, we should see Earth's earthquake epicenters, that's where earthquakes begin, concentrated where these blue lines are, correct? Now, in the 1970s, the big four of seismology, seismology, here's a word you need to remember. Seismology is the study of earthquakes. A seismologist is a person who studies earthquakes. So seismologists hypothesize if plate tectonics is true, we should see earthquake epicenters concentrated where these plate boundaries are, not in the center of plates. And in the 70s, the big four, it's the United States, China, Japan, and the Soviet Union, combined their data to see if that was true or not. Even though it was the Cold War, we combined our data. And let's take a look at it. Wow, look at that. Look at those red dots. See if I can get a bigger picture of it for you here. Oh, holy mother God. Okay, let me just. Okay, look, you can see it from here. Look at that. Do they follow the plate boundaries? Yes, they're exactly on the plate boundaries. 99% of the Earth's earthquakes occur at the plate boundaries, exactly as predicted by the plate tectonic theory. By plate tectonic theory. More validation for this new theory. Earthquakes occurred exactly where you expected them to occur. I'm afraid my hard drive is going to. Let's see here. It says that my hard drive has got anyway, if it shuts down, I'll just do the rest tomorrow morning. So anyway, um, if plate tectonics is true, we should see a relationship between plate boundaries and volcanoes as well. So let's take a look. Let me ask you a question. If at a subduction zone, an oceanic lithosphere subducts underneath continents, then the let's take a look at a subduction zone again. So you sort of want to visualize this. Um, one thing you could do is go on YouTube and type in subduction zones and seafloor spreading. That might help as well. But let's take a look here. At subduction zones where oceanic lithosphere subducts under continents, Do you think that this oceanic lithosphere, as it goes deeper into the earth, makes earthquakes? Do you think it would heat up? Does it get hotter as you go deeper in the earth? Yes. So eventually, this subducting oceanic lithosphere would melt, and it would make magma. The magma, being buoyant, will rise and form volcanoes, right? So if plate tectonics is true, we should see volcanoes occur at subduction zones. Let's take a look and see if that's actually the case. A person who studies volcanoes, he or she is called a volcanologist, and they would know that volcanoes and plate tectonics match up. Let's take a look. Look at that, ladies and gentlemen. Deep ocean trenches mark where the subduction zones are. Here's the subduction zone going all the way down the west coast of North America and South America. We have volcanoes in western South America and western North America where these trenches are. And here in Japan and in Kamakacha in Russia and the Philippines and Indonesia and New Zealand, we have deep ocean trenches. That's where these blue lines are. So we have most of the world's volcanoes occur at subduction zones. Some of them do occur at mid-ocean ridges, making new sea floor as well. So that the volcano evidence matches up with the plate tectonic theory. The earthquakes, the age of the sea floor, the paleomagnetic stripes, everything matches up. By the 1980s, almost everybody had been converted to this new theory of plate tectonics. Once again, don't forget that what the lithosphere means. The lithosphere is the crust in the uppermost part of the mantle. That's what the plates are. If the lithosphere is topped by oceanic crust, we call it oceanic lithosphere. If it's topped by continental crust, we call it continental lithosphere. Beneath the lithosphere is the partially molten asthenosphere. We're in the mantle now. And the very bottom of the mantle, right next to the outer core, that's called the mesosphere, M-E-S-O sphere. Then we have the mantle, made of that rock peridotite we talked about earlier on. The liquid outer core, made of liquid iron, and then solid iron. That's the interior of the Earth. We'll talk more about how scientists figured that out. How do we know that this is down there deep underground when no human being has ever seen it? Well, we know from seismological data, which is very accurate. You know, when you go to a doctor, um, let's say your doctor gives you an x-ray, and the x-rays bounce off the bones in your body, and he can see inside your body. He can see if you have a tumor or if you have some other a fractured bone. Well, when earthquake waves go through the earth, they reveal the interior of the earth. We talked about the crust already. We have oceanic and continental crust. Which is thicker? Continental crust is. Which is denser? Oceanic crust is. Oceanic crust is made of basalt or basalt, B-A-S-A-L-T. And the oceanic lithosphere will subduct underneath the continental lithosphere at subduction zones, forming deep ocean trenches. Okay. So, last thing I want to talk about tonight is there are three kinds of plate boundaries. Three kinds of plate boundaries. There are three main kinds of plate boundaries. And this picture will help you visualize it. If two plates are moving apart, such as at mid-ocean ridges, we call that a divergent plate boundary. If the two plates are pushing together, such as at subduction zones, we call that a convergent plate boundary. When two plates slide next to each other, we call that a transform plate boundary. Try and visualize that. Don't just memorize the words. Try and visualize.